Okay, everybody, we're going to take a very different direction now. Up until now during the semester, we've been talking about regression models, and all the regression models take some type of response variable that we're interested in and correlate them with their independent variables. This is very powerful. It's old traditional statistics method going back a long time. It's very well understood. We can validate them. So we really like regression models. However, they require us to have good response data and good data to correlate with the response. And also, they're somewhat limited in that it has to have that type of a situation where we can correlate a response variable to some other variable. There's a whole group of things that we would like to model and need to model. Like here, you're seeing a picture of caribou migrating through Canada, and then we have a couple of wolves who are hunting the caribou. And as you take a look at this, you can see that there are, to me, fascinating spatial patterns going on. The way the caribou moves, and in a minute, the way the wolves move is very intriguing, and there's definitely structure there. There's patterns that are followed, and this is something that we can and have modeled this type of spatial relationship between things like wolves and caribou and the landscape. And that's what we're about to step into. They're called spatially explicit individually based models. They're within a category of models called agent-based models, where in this case the caribou and the wolves would be the agents moving across a landscape. And the very general area for this would be simulation. So this is completely different from regression. We use a different set of tools and methodologies. But it's for these problems where it's like there's no obvious regression here, right? How would we regress the wolves against the caribou and how they move? You can see the caribou moving across the landscape almost like water moves. And here's the wolves following in the tracks of the caribou that the caribou have dug into the permafrost. And I just invite you to keep watching this video and look for those patterns and think about, well, how would we model this? How would we model it? And of course, it's not repeatable, right? The wolves aren't going to do the same thing over and over again. There's a general approach that they're taking, but then there's this stochastic element, especially in whether or not they're successful in the hunt, but where the caribou run, where the wolves run, those interactions. So there's patterns. In other words, there's what we would look for as a trend in regression, but there's definitely patterns going on in the system. And then there's a random effect as well. So these are, again, very mechanistic models that have a predictive component. And then there's a high level of stochasticity or randomness in the model as well. In this particular movie, the wolf is successful at cutting out a younger caribou. But in most cases, the wolf is not successful. Okay, so feel free to watch that a couple times, and I will move on with the rest of the presentation. So in general, this is the area of simulations. So this is something where we model something in the past or potential events. They're usually not considered to be generalizable, although some simple models may be. And this really relies upon the knowledge of the mechanisms behind the processes that create the event. In other words, this is not based on response and covariate data. This is based on really understanding or believing we understand the mechanism. Down lower right, there's actually a simulation of emergency response folks being trained in a 3D environment. And this is being heavily used now in nursing, the medical industry, response, because we can, using 3D hardware, electronic hardware, we can simulate all kinds of different situations that emergency folks would not see normally during their school time. And they can simulate it, and then they can respond to it. And so they can learn in this 3D environment. And these are all very sophisticated simulations. Similarly, there's lots of simulations around things like volcanic eruptions, because those don't happen very often. And a whole group of people research not only volcanic eruptions on the Earth, but on other planets as well. And they make simulations because they don't get to watch a lot of them. Species population dynamics, it's another area used. Disease propagation, which we'll talk about. Flood dynamics, social dynamics. This is used heavily in social systems for the movement of people as well as other issues with folks. Earthquakes, oil spills, and landslides. I've done quite a bit of work with oil spills in the past. So the problem is, how do you validate these? And this is really the big if for this, is if you have past events, you can ground truth it, but how generalizable it is. In other words, if you can create a model that recreates an asteroid impact on the Earth that destroys the Earth, well, great. Does that recreate exactly what happened? There's lots of different things that could have resulted in the same data that we have on the Earth for past asteroid collisions. So it's not truly validatable, and that's really a big issue with these. If you're predicting in the future, climate change being the classic case, how do we ground truth that? Well, they ground truth it by going to the past, but nothing like what has currently happening now with the Earth, with carbon emissions, has ever happened in the past. So they try to find things that are similar and look at what happened, but we really don't have ground truthing for it. The best case, model what's happened on past events, ground truth it off of that, or test your models, and then extend it into the future, but be careful on the conclusions that you draw from it. Civil engineering, which is part of my background, is heavily based on what works in the past. In fact, civil engineering is based on a lot of theory of materials and the dynamics and static physics of materials. But then people built things and they fell down. And so then you have books that talk about the margin of error based on what's fallen down and what hasn't. I say fallen down, but it could be all kinds of different failures that occurred. One of the most famous is the Tecumseh Narrow Bridge disaster. Hopefully we won't get an ad here. Yes, we got an ad. Thank you, YouTube. So I'm going to skip over that ad as quickly as I can. Meet your new instructor. So this is a famous example of a bridge that was built, and it was built using established, well-known techniques and analysis for building suspension bridges. But it started wobbling, and eventually it wobbled back and forth quite a bit. Okay. And eventually it collapsed. And what they learned from the Tecumseh Narrows Bridge was that there were winds blowing through this canyon that were at a certain speed. And the speed of the wind created a harmonic oscillation in the suspension bridge. This had never been seen before, certainly never videotaped and recorded like this before. Well, civil engineering learned, now when you build a suspension bridge, you have to look at the wind velocities and the harmonic oscillation of the bridge and make sure that they don't match up like this and have it collapse. So it's not that we can't use these types of simulations. In fact, civil engineering is heavily based on that. Anytime you build any major structure in civil engineering, you have to create a simulation and test out your structure, a simulated version of it. Nowadays on computers, often they still use physical models, and but traditionally it was physical models would be built and then put under all kinds of different stresses. So that's kind of how you test these. You never can test it for real, but you can get close. NASA does a bunch of simulation models about movement of the ocean, movement of atmospheric particles, all kinds of things that are very impressive and fun, but I'll leave those to you. There's also a difference between an animation and a simulation. If you're like me, you may watch a lot of disaster movies. And so here we have water hitting a city, but this is done in a 3D animation package. So this is a little different. This is more like what you would see in, a 3D movie at the theater, where they are creating an animation of it. It's using some information. Oh, another one, all kinds of good stuff. Highly recommend playing with this. Okay, so here they're using the dynamics of water to show how water moves, which is pretty cool. Kind of a simulation, but more of an animation. So anyway, there's a lot of good stuff that happens. This asteroid impact one is pretty sensational. So the wrap up here is when to simulate. So if you're just doing a completely hypothetical scenario, asteroid hitting the Earth, aliens visiting the Earth, whatever, something bizarre, but also something very pragmatic as far as the land manager goes. Maybe prescribed burning. You might want to simulate burning and then simulate what would happen if, what if there was a big wind event while we're doing our prescribed burning? What could happen? So that'd be hypothetical. Really minimal data. This is one of the biggest ones for us, is if you don't have enough data, you do a simulation. And then again, we're just careful with the conclusions we draw from that, but you can then simulate all kinds of cool things. Temporal processes, these not only produce valuable simulations, but also compelling animations. And it's also where the process is believed to be well understood. So in other words, we're looking for mechanistic processes that we feel like we understand pretty well so that we can build those into our model, as opposed to a relationship between a response and a independent variable. It's also when the problem is simplified enough to run on available hardware. The hardware is almost always a limitation. In other words, the number of computers, the amount of time you have. And also they're very educational. So disaster scenarios, earthquakes, the tsunamis you just saw, great educational things. I learned more in 15 minutes from one of my students' animations showing how volcanoes worked than I had in the previous rest of my life about volcanoes. It was excellent. And I'll stop.